All right, hello, and welcome back to next video, solving problem number 2 of the final exam for ESE 403. Here we have a problem rooted in finance, but it's actually solved as a minimum cost flow problem. So we have Jake, who is trying to pull money out of 3 different foreign currencies, specifically the Japanese yen, the Indonesian rupiah, the Malaysian ringgit, and trying to get that to USD. We're given exchange rates, we're giving transaction costs, and we're also given transaction limits as far as how much money that can be pulled. But the way we're going to formulate this is actually as a minimum cost flow problem where each of the legs is going to be the transaction cost. In fact, and then the leg constraints are going to be the transaction limits. And then for as far as currency exchange goes, it's actually not that important to the problem. It's only important in understanding how much of their holdings is actually in USD so that the whole problem can be solved just in USD, which makes everything a lot simpler. For example, our transaction limits are given in USD, and so that's the only thing we use it for. So without further ado, we're going to take a look here at where we started. So for example, really the first thing I wanted to do was convert everything to USD and understand what we were dealing with and what needed to be transferred into the United States. And so we see that the rupiah holdings are going to be about 1.6 million, ringgits are going to be about 5.6, and then the yen is the largest at 9.6. And that's all done using the conversion rates and the amount that the problem states. Yen has to be converted from the starting point when they had a $15 million holding at $1 equals 80 yen, then to today. And so based on that, we know where to start. So we know what our sources are, and we know that the end, the sink, is going to be the USD output. And so this is the most complicated it can possibly get, is this chart here where every single currency can be converted into every single other currency. And that would be quite a problem to solve, because that would create upwards of 40 to 50 different decision variables, which is not easy to deal with, because each of these flows is bidirectional. So the arrows showing that they're flowing both ways, not just one from the other, but both ways. Of course, we have the different sources. The new nomenclature, of course, I should have said earlier, yen is 1, 2, 3, 4, so on. This is going to simplify the notation later in the problem. But I do want to make a few notes about the formulation, which is actually going to simplify things for us. So like I said before, all values are going to be in USD, since the exchange rates show that $1 USD is equal to $1 USD in the other currency. What does that mean? Basically, there's no arbitrage. It's that no matter how you convert the money, it should always come back to the exact amount that you expect it to. And because of that, we can assume that we can just kind of more or less toss out the exchange rates as being a true variable. Secondly, and probably most importantly, is that by visual inspection of this table, we can determine that there's no more efficient way to move between the Canadian dollar, the euro, the pound, and the peso and USD besides going straight from that currency to USD. What does that mean? It means if you're in euro, and you're trying to get to USD, you're always going to go to USD. You're not going to go from euro to Canadian dollar and then to USD. That would not save you money. And in no case would you save money in transaction costs by doing something like that. So all of a sudden, the problem actually gets quite simple. And so we get a formulation that actually looks like this, where you have much more simple flows. Of course, those sinks, the sources rather, the ringgits, the yen, and the rupiah are all going to need to flow to each other because they have transaction limits. But because those other four, the Canadian dollar, the pound, the euro, and the peso don't have transaction limits, we know that in the optimal solution, those are only going to flow to USD. And so here we can see that those are only one directional flows, and they're only receiving flows from those 3 sources. They're not receiving from each other. They're not sending back to the other sources. And so this all of a sudden becomes quite simple. So labeled here are the percentage transaction costs in their decimal representation, because our variables are going to represent the total amount of money that is being transferred through those flows. And then here we have the total, each of the sources, and the total we expect to receive at the sink. And finally, the transaction limits, where, for example, between 1 and 2, that's ringgits, that's yen and rupiah, actually, you can't transfer more than $5 million. Great. So now that we have this, we can actually move on to our LP formulation, which then we can use an IBM DOC. We get this minimization function because we're trying to minimize the total cost, right? And so, like I said before, X12 is the total amount transferred from currency 1 to currency I to currency J, right? And so we're going to have all of the transfer costs times the amount transferred. Then, as far as our constraints are concerned, it's going to be the node balance. So, for example, we want to have everything kind of adding up. So everything coming into 5 must equal what is out of 5. Everything that is into 3 must be equal to what is out of 3. And so we're able to do this just by summing the different flows. We know what everything should be. Those transport nodes should always equal 0. The sync node is going to be negative, and those sources are going to be equal to the positive, because we know that inflows are negative, outflows are positive. And then finally, we have all of our transaction limits, and those are going to be the most complicating factor. Really, finally, is the non-negativity, where all of our flows are going to be positive. We can't have any negative flows. So this is going to be formulated in IBM DOC. So here is that formulation. Again, we have quite a few variables. Here's our minimization function. Here are the constraints for balancing the nodes, and then our transaction limits down below. So part B of this problem, so actually we'll discuss the solution first. So the solution here is that Jake should convert 2 million USD worth of yen to USD, 2 million USD worth of yen to Canadian dollar. So after they've converted to USD, Canadian dollar, pounds, pesos, euros, then they can convert from those other transport nodes to USD. So here are the values that they should convert out, and it just all should add up. There's nothing really new about that. This is going to come to a transaction cost of $74,000, and that will leave Jake with around $16,800,000 USD to invest in U.S. bonds, because of course they're losing. That's a cost. They're losing that from their total holdings. Now, problem B is asking us what happens if there are no transaction costs. Transaction limits. This is pretty easy to reformulate. We have the exact same minimization function and almost the exact same constraints. We just lose all of those transport limit constraints. And so then we just end with our non-negativity, again, formulated in IBM DOC, but without all of those limitations. Now, if we run this, we will see that we get a different optimal solution, which is to be expected. In fact, it is quite a bit more cost efficient. It's only costs $42,000. We see that we transfer only a couple of times. Specifically, we are converting from yen to pounds, rupiah to Canadian dollars, and ringgits to Canadian dollars. And then we're converting out of Canadian dollars and out of pounds. The total transaction cost is only $42,000-ish, and it will leave Jake with $16,837,000 or so USD to buy bonds. Now, in part C of the problem, we are now told that there's going to be a 500% increase in the transaction of all rupiah. And so what is that going to mean? Well, it means that we need to multiply all of those transaction costs that have anything to do with rupiah, in this case of the formulation, anywhere that there's a 2 in the subscript of the x variable, you're multiplied by 6. And that is just, fundamentally, that's 500% increase is times 6, right? So 1 plus your percent increase, well, it's a 500% increase, so it's 5. So 1 plus 5, 6. So here's our new minimization function. That's really the only thing that's different, though. Again, I didn't bother to write out the rest of the constraints because we share the same constraints as this formulation, because there is no transaction limits per the problem, but there still, of course, are those node bounds. So this is all we really have to worry about here. So again, this is what it looks like formulated in IBM DOC. Again, same thing, but you can see that we have multiplied 6 in front of any of the variables that have a 2, because those means that they're dealing with the rupiah. Now, this solution actually is not going to have any different flows from the solution without transaction limits. And the reason for this is because there is no more optimal way to really send the money. All you're going to have is a difference in the total amount of transaction cost, right? It's going to be 6 times more when dealing with the rupiah, right? Because if we think about it, in our first example with the no transaction limits, then you're always going to probably send your money kind of through one way, right? Because there's no reason to, you're just going to send it through the cheapest route out of the country. So in the same case, you're going to always send it through the cheapest route out of the country now that there's no transaction limits. So now you just pay that extra premium on the transaction cost. So here we see the exact same flows, but the total transaction cost is now $67,000. And so it's going to leave Jake and his company with 16,812,000 USD to invest in bonds. Just want to go over some more theoretical things. What are the things that Jake should consider as part of the problem that he's not currently? And so really one of the most glaring issues is, are there transaction limits on euros, pounds, pesos, and the Canadian dollar? If there were, the LP would change completely. It would be much more complicated, as I said before. And then also, are the exchange rates stable? If the exchange rates aren't stable, then the cost is going to change as you are making the transactions, and that could really change how you might want to send your flow. You might want to wait to make the exchanges. You might want to put them into a different type of asset. Could the collapse have rippling effects across the country, or across the world rather, and change exchange rates in drastic ways that change the formulation of the problem? And are there really arbitrage opportunities in the market which would allow money to be made through transactions? Those are not out of the realm of possibility. In fact, a lot of people, exploit those, and banking today, and so that's definitely on the table. So there's a few more things that I thought Jake should probably consider before he makes his final decisions. But I think this is overall a pretty strong flow program for him to follow in order to get his money out of Japan and other Asian countries as quickly as possible. So that's it for problem 2. Thanks so much, and I hope this was a good explanation of how to solve problem 2.